Hello. So in today's video, we will talk about the complexity of algorithms using frequency counts, and we will be using sorting algorithms to demonstrate this. We will first talk about complexity, then about sorting algorithms for this presentation, after which I'll explain the experimentation setup and analyze and discuss the results. Finally, we have the conclusion. The complexity of an algorithm tells us how good an algorithm is based on how fast it performs a given task. If you have ever heard of the term Key Performance Index or KPI, well, this is the KPI of algorithms. The lower the complexity, the better. To be a bit more technical, this is how long an algorithm would finish or the number of steps an algorithm would make given an arbitrary input size, usually represented as n. The big O notation is typically used to represent complexity because it accounts the worst case complexity of an algorithm. O of n squared means that the time it takes for an algorithm to finish grows quadratically as input size increases. And the O of 1 means that the algorithm takes the same number of steps regardless of input size. A while ago, I mentioned that we'll be analyzing sorting algorithms, but what are they in the first place? Sorting algorithms are used to rearrange the elements in the list based on a comparator, most commonly greater than or less than signs, to arrange elements in descending or ascending order. Here is our experimentation setup to show how complexities work through sorting algorithms. We will be running 6 sorting algorithms, namely bubble sort, insertion sort, selection sort, merge sort, shell sort, and quick sort. All the function implementations in the code return an integer representing the number of steps that occurred during its runtime. They also aim to sort the list in ascending order. For each of the sorting algorithm, we'll have 3 cases of input: a randomly generated list, a descending ordered list, and an almost sorted list. Here are how the inputs are generated. So we have x, a list of desired sizes, which are just increasing by a factor of 2 from start to end. We first generate random lists which have sizes indicated in x. Okay. That set of lists is then assigned as the first element of A. The second element of A is the same set of lists as the generated ones, but they are all sorted in descending order. The last element of A is also used as the first element of A, but they're all 90% sorted. A will be used for the experiment, and its contents will never change all throughout. Let us now begin with bubble sort. As you can see here, the count is incremented for every comparison done. Meanwhile, a swap increments a counter by 3 because it is usually done in 3 steps using lower level languages like C and assembly. We can see here that the complexity of the algorithm is O of n squared due to the nested for loop, one going from the length of the array down to 0, and the inner loop going from 1 to I inclusively. In this graph, we have the blue line representing n squared over 2, and this will serve as our basis. For the unsorted case, the graph in the table proves that the algorithm is indeed O of n squared. As the input size doubles, see here, the number of steps it takes to sort the list is more or less quadrupled. For the descending ordered case, the gap between the basis and the actual frequency count became very large. This makes sense because descending ordering of the elements causes the algorithm to keep swapping elements, hence a greater number of steps, and nonetheless, the algorithm still has a quadratic growth rate. For the almost sorted case, the gap between the basis and the frequency count is minimized. In the previous case, the swapping occurs frequently, but in this case, it is minimized as most of the elements are already sorted. But even at the best case, you can see that the algorithm is still O of n squared. Now let's move on to the next algorithm. Here's the implementation of the insertion sort. We increment the counter for every comparison done, and another increment for replacing the elements. We have a plus 2 here to count this statement and this statement, both assignment statements. The complexity of this algorithm is also O of n squared due to the nested for loop, one going from 1 to the length of the array and the other going from j down to 0. We use the same basis equation as before, which is n squared over 2, and we can see that the frequency count is almost tied to it. So insertion sort does have an O of n squared complexity. When the list is sorted in descending order, the gap of the basis and frequency count became larger. This happens because elements are also moved a lot because the if statement always fails here. So the break is not called and the for loop continues. This also has a greater frequency count than bubble sort since they basically do the same thing at this arrangement, only that the insertion sort has done more steps in each iteration. In the almost sorted order, the frequency count is minimized as the break statement is executed more often. In fact, when the array is already sorted, it does just one pass. Hence, it becomes linear complexity at best. Let's move on to the next algorithm, which is selection sort. This is the implementation of the algorithm. It has counters for each comparison and another counter inside when the assignment statement runs. The counter is incremented by 3 to consider the swap element here and another assignment statement here. That's why it's incremented by 4. The complexity of this algorithm is again O of n squared due to the nested for loop, one going from 0 to the length of the array and the inner loop going from I up to the length of the array. In the unsorted list, the algorithm's time complexity is O of n squared as seen in the graph and table. In the descending ordered list, the selection sort performs almost the same as that of the unsorted one here. Unlike the first two algorithms, which have the worst case when the list is in descending order. This makes sense as selection sort compares the chosen element to all other elements left in the list first before making a single swap. In the mostly sorted list, the gap between the basis and the frequency count became a lot smaller because the conditional failed more often. Hence, the reassignment statement was less executed. From what we've seen, the selection sort is not much affected by the ordering of the elements in the list, unlike the first two algorithms. So let's move on to the next algorithm. So this is the implementation of the merge sort. The count is first initialized with the length of the whole array because a deep copy operation was performed. Okay. For the left side of the array and the right side of the array, the +2 came from the conditional here and the assignment statement here. Okay. So in this while loop, the count is incremented by 4 because a comparison was done. So that's one step. And in both if and else body, there are two statements. So worst case, there are 3 steps done in this group. Then finally, we have an increment, which increments the counter by 4 entirely. Okay. The last two loops have only 3 increment to the counter because no more comparison step is done. Instead, the statements are done directly, immediately. Okay. So this is a divide and conquer algorithm and has a time complexity of n log n. In this graph, the basis is now 5x log of x. In the unsorted array, the growth rate of the algorithm is n log of n. This is a huge improvement, as can be seen in the biggest n in the table. The frequency count is less than 1 million, while selection sort almost reach 50 million steps here. Okay. This is a huge improvement. So in the descending ordered list, the algorithm performs a bit better since the frequency count went just a bit below the basis line. Okay. This happens because the first while loop finishes as soon as possible, as it empties out one side of the array, and moving on to the next set of while loops that have no extra conditionals. Okay. From the explanation a while ago, this graph is also expected in the sorted array because most of the array is already sorted. While we can see that the values of the frequency count are a bit higher than that of the reversed, there is still some because there are still some unsorted items here. But from what we've seen, the merge sort, similar to selection sort, is not affected by the ordering of the elements of the input list. But having an already sorted list, whether regardless if it is in reverse, will yield a slightly better result. Next is shell sort. Here's the implementation of the algorithm. We can increment the counter here by 2 to consider the two assignment statements. It is also initialized to 2 of the two assignment statements here. And finally, a 3 here to consider the three assignment statements here at the outer for loop. And finally, a +1 to consider the interval update. The average complexity of this algorithm is O of n log n, and the worst case is still O of n squared, which only happens when the interval is initially set to 1, which effectively makes it a plain insertion sort. In the unsorted array, we can see that the frequency count is comparable to O of n log n, even if it has a worst case complexity of O of n squared. For the descending sorted set, the performance was even better than the unsorted. That's because the algorithm is able to efficiently switch the elements from the rightmost to the leftmost and vice versa. But the best case would be achieved when the array is already sorted in the right order since no swaps would be made. For the mostly sorted set, the performance is almost equal to our basis. This is a result of the remaining unsorted 10% causing numerous inefficient swaps in the process of the algorithm. We have seen from the graphs that shell sort performs a lot better than insertion sort since it minimizes the number of shifting by swapping off far off elements immediately. So unless the interval is badly set, the expected complexity of the algorithm is O of n log n. Finally, we have the quicksort. The implementation has an inner function named partition that returns the index of the partition and a counter. It is called here. Okay. The count is first initialized to 2 for the assignment statements, and then is incremented by 4 due to the assignment statement and the swap operation. Finally, a last swap is done, so the counter returned is incremented by 3. Okay. The algorithm has a complexity of O n squared, and this would be visible later. Note that the basis in this graph is still 5x log of x. In the unsorted list, we can see that the growth rate is comparable to that of n log n. Quicksort is similar to merge sort as it performs partitions. Ideally, it would be able to partition the list to 2 equal partitions every time. It will then be a divide and conquer algorithm. However, in the case of a sorted list, whether it is in reverse or not, quicksort will be very inefficient because partitions will result in one element being sorted for each pass. Hence, its worst case time complexity is O of n squared, even resulting in a greater frequency count than bubble sort. In the almost sorted array, the growth rate is surprisingly comparable to n log n. One would expect it to be slower since 90% is already sorted, but it still yielded a decent enough frequency count. To conclude our session, here is the summary of what we have found from the performance of these sorting algorithms. Bubble sort has a complexity of n squared all throughout, but the more sorted an array is, the less swap operations are done. Insertion sort at best is a simple linear pass when the array is already sorted. Worst case is achieved when elements are inserted at the first part of the array, causing all the other elements to shift, and this happens the most in descending ordered arrays. Selection sort is not affected by the initial ordering of elements inside the list and will always result in O of n squared, but it will perform better than insertion sort and bubble sort when the input list is sorted in descending order. Merge sort is not also affected by the initial ordering of the elements. It just keeps cutting the list in half and performs a linear time merge operation. Shell sort usually performs at n log n time. It highly depends on the initial interval set in the algorithm. For example, an initial interval of 1 will essentially make it an insertion sort, which makes it an O of n squared algorithm. The best interval is yet to be found, but it performs at n log n time. Quicksort highly depends in the initial distribution of the data. An already sorted input will result in the worst time complexity because it only sorts one element in each pass. In the best case, it manages to split the list into two equal parts, similar to merge sort. That's it for my presentation. I hope you've learned a lot and see you in the next video.